Okay, so good, very good.
Vabbè, fate come volete, siete grandi tutti e due. Sì, magari
Mi metto qui anch'io perché sennò sì. Ok, so welcome everyone to colloquium today. Our guest speaker today is Professor Massimo Della Valle, who hardly needs any introduction from any of you. In any case, I will say a few words about Massimo, who graduated in Padova and then moved for a short experience in Trieste. He's been working, actually, his PhD he got in Armenia.
Soviet Union,
Former Soviet Union, Burakan, observatory of Burakan. And then he worked for a long time for the ISO, both in Garching and Chile, where he did a huge amount of work on transients, supernovae in particular. Then he moved back to Italy. He got a position, he started a position in the former Observatory of Padova, which is still Observatory of Padova, but now INAF. Moved as an associate astronomer to Arcetri, and as of 2008, he is a director of research in Naples, which he also directed. Observatory of Naples, of which he's been a director. Massimo has been working. Massimo is, by the way, a knight of the Italian Republic and a member of Accademia dei Lincei. His work needs very little words, and because it enjoys a lot of recognition worldwide. He's been working virtually on every type of transient, starting with supernovae, but he gave a significant critical contribution to gamma ray bursts, the study of gamma ray burst, supernova connection. In supernovae, he's an expert of both thermonuclear supernovae and the core collapse supernovae. However, he is also a leading expert in nova explosion, which is the subject of his talk today. So thank you very much. I will leave the floor to Massimo.
Okay, thank you, Elena, for this rather nice introduction. Just a word in Italian. Non dico mai che sono cavaliere perché in Italia non è proprio il maestro.
Lo dicono gli altri.
No, ma però è successo, sono contento. Grazie. Okay. Thank you for the kind invitation, and I have seen a lot of persons that I know very well, Nicola, Angela, Liana, mythical cast. So, but now it's a pleasure to meet you on person. Okay, this is this should be the doesn't work.
Ma un giorno funzionerà tutto, no?
Yeah, five years ago it was working perfectly, and now it's not. Okay.
Okay, if you try here.
No. Just
Oh, sorry, try.
No.
Try again with this one.
Okay. Okay, thank you so much. This is the summary of the talk. I start with a short historical background, basics of nova phenomenon, nova population rates, galactic lithium problem. This is one of the hot topics in astrophysics related to classical novae. Novae as lithium factories. There are two more aspects that I would like to highlight. Nova has progenitor of Taiwanese supernova. It's quite embarrassing that today, when we use Taiwanese supernova to claim about this dichotomy with the Planck measurement of each knot, we still don't know. We don't know if Taiwanese supernova produce by single degenerate systems, double degenerate, or maybe both channels are at play. And the other point is from in 2010, Fermi has detected novae as a high energy sources. Filippo will forgive me if I cannot go into also this topic, because I think the first 5 will take up all my time. However, for people that are interested, I recommend the Livio and Paolo Mazzali review on progenitor of Taiwanese supernovae. There is a paper with Yale Hillman and Daphne Guetta that we are going to submit in these days on the same topic. And for novae as high energy sources, I recommend this comic I told you, review paper, very detailed, fantastic. And concerning the high energy neutrinos that could be emitted, there is a recent paper by Daphne, myself, and yeah. Okay, novae has played a pivotal role in the so-called great debate between Alan Shapley and Herbert Curtis about the intrinsic nature of nebulae. From 1880 to 1925, several dozen of nova stars were discovered in nearby galaxies, M31 and GC 4321. Well, Herbert Curtis used novae to support his ideas that these nebulae were far away, were a very distant system from Milky Way. And look at what he writes here. If we assume equality of absolute magnitude for galactic and spiral novae, then the latter being apparently 10 magnitudes the fainter, that means out of the order of 100 times as far as the former. 10 magnitudes means a 10,000, a factor of 10,000 in terms of luminosity, so at 100 factor in terms of distance. That is, the spirals containing the novae are far outside our stellar system, and these particle spirals without any doubt. What happened? That in 1885, there was a strange nova occurring in Andromeda. That now it turns out to be a supernova indeed, many decades later. And so this object achieved a magnitude of 6 in Andromeda. And so that gave the opportunity to Shapley to say that Curtis was wrong. Why? Well, because we never observed, if you are right, and we considered Andromeda at the distance that you claim, these nova in Andromeda should have an absolute magnitude of minus 16. And there are no novae in our galaxy with such a high luminosity. So hence a stellar luminosity of this order seems out of the question, and according to the close comparability of spirals containing such a nova to our galaxy appears inadmissible. Well, we know how the story ended. Hubble discovered a variable star. He believed it was a nova, in fact, was a Cephei. And so at that point, we are in 1925. So all the works by Mr. Leavitt were already well recognized. And he wrote immediately a letter to Shapley. You will be interested to hear that I have found a Cephei variable in the Andromeda nebula. And when he opened this letter in his office, there was present his PhD student, Cecilia Pagaposchi. And she reported that the comment of Shapley, here is the letter that destroyed my universe. And I recommend to you to read this paper, this book, if possible. Is the biography of Cecilia by Pagaposchi, What Stars Are Made Of. It's not my book. I want to emphasize this, otherwise the director start to ask me il pizzo subito, ma questo è un altro paio di maniche. I know who was telling, I know my chicken. Okay. And the dispute between the luminosity of nova and supernova ended in 1934 when Valle and Zwicky introduced the concept of supernovae. With all reserve, we advanced the view that a supernova represents the transition of an ordinary star into a neutron star consisting mainly of neutrons. Such a star may possess a very small radius and extremely high density. One of the most, let's say, incredible prediction that have been done in astrophysics. So nova phenomenon is very similar to supernova phenomenon from a phenomenological point of view as a sudden appearance in the sky of a new object, but they have a completely different energetic scale, 10 to the 45 erg versus 10 to the 53 erg. The time scale are compatible, as you see, a few weeks. And obviously, after the big clash or the big crash due to the misidentification between nova and supernovae that delayed considerably the knowledge of the cosmic distance scale, nova were dismissed for several dozen of years. Well, they were back in the 50s and 60s when they provided, through the binarity and the accretion in a degenerate environment, a nice mechanism to explain how it was possible there was a stellar explosion in very old stellar populations. And this is due basically to the paper by Schatzman in 1951. He was telling for the first time that, look at, say, puisse se former une onde de détonation. That is started to understand to explain the nova phenomenon, the ejection of these shells through this onde de détonation. Robert Kraft are all nova binary stars, and then an important paper by Podor Paczynski, cataclysmic variable among binary stars. So boosted by this theoretical interest, people start to observe, to start surveys for nova searches in external galaxies, basically M31. Consider that novae explode in all Hubble-type galaxies, in spirals, irregular, in elliptical, in lenticular. So this point was natural, in spite of the unsuccessful result at the beginning of the century, to use them again as a standard camera and to measure the cosmic distances. What about we know today for classical nova phenomena? I try to summarize in a single slide what is going on. I hope to be clear enough. So we have a white dwarf, a binary system formed by the white dwarf plus a low mass main sequence star. In some cases, is not a low mass main sequence star, but is a red giant. The secondary accrete material onto the white dwarf, and when the pressure at the bottom of the crater layer is of the order of 10 to the power of 19 dynar per centimeter square, the hydrogen start to burn at the beginning with the proton-proton cycle, but immediately switch to the CNO cycle. in the CNO cycle, the dependence of the energy production on temperature is a very high, to the power of 16, compared with the proton-proton chain that is to the power 4. So the ignition is explosive. And consider that we are in a degenerate environment, so temperature and pressure grow up without talking to each other. So there is not the possibility for the expansion to prevent the dramatic increase in temperature. And this process led to violent thermonuclear array. Basically, look at this. This is a typical CNO cycle, and this beta unstable nuclei are transported by the convention on time scale of the order of a few minutes to the surface, to the outer part of the layer, accreted layer. In this case, obviously, after 7 minutes, for example, in this case, the nuclear decay energy is released, and this is enough to eject the accreted shell with the expansion velocity between 500 and 5,000 kilometers per second. In supernova, this expansion velocity are of the order of 10,000 kilometers per second, but could be easily 30,000 kilometers per second. When you look at novae, you can they are characterized by a very high degree of individuality. There are very intrinsically bright objects, -9, for example, characterized by a fast decline, and -6.5 in this case, so remarkable fainter, a factor 15 in luminosity, characterized by a gentle decline. And this relation between absolute magnitude maximum rate of decline was calibrated by an impressive number of astronomers in the past, even of the most used calibrated relation has been elaborated by myself and Mario in 1995. The choice of the colors is not random, has been inspired by recent events. Did you understand this? Perché adesso dico italiano, sono stufo di vedere ogni volta che Tommaso Belloni fa un talk che mi fa vedere tutti i talk rossoneri. Adesso passiamo all'offensiva. What is important is that, look, we are at -9. Well, -9 is like the most the brightest Cepheids. Cepheids are good distance indicators. So at those time, we're talking about 1995, so 30 years ago, almost 30 years ago, we decided to use Taiwanese novae as distance indicators, and they have the advantage with respect to Cepheids to explode any Hubble type of galaxies. And so, for example, we have compared our calibrated relation with the relation found by Pritchett and Van den Berg, observing novae in Virgo, and of course in apparent magnitude, and we compare the apparent magnitude with the absolute magnitude, derive the distance modulo, and from that, the distance. And that's why, for example, that was our measurement, 70 plus -13. So I'm pretty happy today about 70, but what is really unhappy, I'm still very unhappy is that this is 20% uncertainty. And that, I mean, makes a novae not anymore competitive. Obviously, when I was student, the dichotomy was not between 67 and 74, as is no, not a little bit different. It was 50 and 100. Alan Sandage, Gerardo Couleur, Sidney Van der Berg. Okay, and so today is okay. At the time of this plot was 4.4 sigma. The tension now is of 5.5, and in the era of cosmology precision, where the uncertainty on the Hubble parameter is of the order of 2%, you easily understand that 20% is useless. I check again this point in a review paper that I wrote with Luca Izzo, and we compare the measurement obtained by the MMRD, the Massimo magnitude rate of decline relationship, the one calibrated with Mario Livio, with the Gaia measurements. And the conclusion is that at the best, with novae, we can achieve a 12% uncertainty in the distance. The still is far from 1-2% uncertainty, which characterizes the cosmology accuracy era. So we dismiss novae for the second time. But then, is still useful, this relation? Yes, it is. Because this relation is the best tool that we have in our hands to understand the properties of a nova outburst. There are an incredible number of papers. I quoted here only is my personal selection, what I consider very basics for nova studies. Maybe there are, I'm sure there are more, but I wrote that just trust my memory. So the physical parameters of the outburst are primarily determined by the mass of the white dwarf, accretion rate, temperature of the white dwarf, magnetic field, composition of accreted material, and all mixing process between accreted envelope and underlying white dwarf. Mario 92 is making this assumption. Well, the driver parameter is the mass of the white dwarf, and this makes sense a lot. Why? Why? Because the amount of material that you need to accrete on the surface of the white dwarf to achieve the condition to start a violent thermonuclear runaway depend on the properties of the white dwarf, the radius and the mass. The more massive is the white dwarf and the radius becomes smaller, this delta M accreted becomes smaller and smaller. And now you easily understand why this relation between absolute magnitude and rate of decline does exist. Because the luminosity is black body luminosity 4 pi r squared sigma t to the 4. R is the expansion velocity times the time from the explosion. I mean, this is a pseudo photosphere is expanding, so the luminosity increased dramatically. The delta M is smaller in this nova coming from massive white dwarf, so the velocity of the jetta are large, and this and this luminosity increased dramatically. Obviously, since the mass of the jetta is smaller, this layer will become transparent very soon. And at this point, this explains why the decline occurs in very short time after the maximum. And the other way, all what I said is true, but the other way around for novae, all that are produced on the surface of less massive white dwarfs. All these facts have an important consequence. The recurrence times, the recurrence time between two consecutive outbursts is determined by the delta M accreted over m dot. M dot is of the order of 10 to minus 8, 10 to minus 9 solar masses per year. Delta M decrease with the mass of white dwarf. So for massive white dwarfs, we have in binary systems that produce the nova phenomenon with the interval time, the delta T between two consecutive outbursts is of the order of 1,000 years, while for less massive white dwarf is 100,000 years. Okay, this is the theoretical relation found by Mario in '92 that I would say that fit nicely the observed data point. The blue are the novae in LMC and the black one, the novae in M31. We can summarize what I just told to you. The more massy is the white dwarf, the more powerful is the outburst. This is the short message. Now, I recommend to you, just that people that maybe like to dig a little bit in the story of astronomy, to this paper by Walter Valle, APJ 1944. This is important because now we use the concept of stellar population daily, but that was the starting point. Valle introduced the concept into astronomy that different kinds of stellar population, which have different properties, metallicity, luminosity, masses, whatever you want, have different spatial distribution within the galaxies. And so if you look, for example, in the nova in M33, you see that these are basically in the arms of these galaxies. There are no one in the bulge. I'm not sure that M33 has a big bulge, but however, the central part of the galaxy have no novae. For M81, for example, you see novae that occur in the arms and novae that are related to the bulge. And when you look at the MMRD in different kind of galaxies characterized by different Hubble types, here with the LMC, M31, and M87, M49, two elliptical galaxies in Virgo cluster, you see that the relation is universal, but what is different is the way in which this relation is populated. Of course, someone can ask, what about the observational bias? Okay, well, that would be a very strange observational bias. Look, in the LMC, that is the galaxy that is nearby one, we see all bright objects and we should miss the faint one. While, for example, in Virgo, that is a 20 megaparsec far away cluster, we don't see the bright object and we see the faint one. So this observational bias is going the other way around. Okay, so this is a physical difference due to the fact that these novae, so come from more massive white dwarf. This is a mixture of disk and bulge, and those are only bulge novae. And this is important. Why? Because when Cecilia Pangaposkin wrote in 1957 the Galactic Novae, this is a classical book, and she did the classification according to the rate of decline. She defined very fast fall of 2 magnitude in 10 days or less, moderately fast 2 magnitude in between 26 and 80 days. And when I was a student, I was asking myself, why 26 to 80 and non 28 to 84? I mean, this is a morphological classification. Now, what I talk to you allow us to move from a morphological classification that is still important, obviously, to a physical classification. And basically, we have defined only 2 classes of novae: the disk novae and bulge novae. That's it. In the same years, Bob Williams, at that time, before becoming director of Hubble Space Telescope, and he was a director of the Tololo Pan-American Observatory in Chile. So I had the occasion to collaborate with him. He ignored completely all this. I didn't know about what I was telling to you. And he found on spectroscopic basis, that there are 2 classes of novae: the iron 2 and helium nitrogen, according to the atomic species that appear in the early stages spectra of novae. And so now I don't want to go into details, but we can take this as a final message. How much time I have?
Quarter of an hour.
50 minutes, okay? Perfect. Okay. A typical this nova is a fast nova whose light curve is characterized by a bright, intrinsically bright Massimo up to -9, and fast decline between the fast nova decreased by 3 magnitude in 20 days, or 2 magnitude in 12 days. Belong preferentially to the helium nitrogen class. And they are located at small height above the galactic plane, 150 parsecs. And this is consistent with the idea that the progenitor were massive stars, probably 6, 7, 8 solar masses. And is related to the oldest fraction of Pop-1 stellar population. So the white dwarf here relatively massive. A typical bulge nova is a slow nova characterized by decline much longer, normally belong to the iron 2 class. And the progenitor extend all the way up to 1000 parsec from the galactic plane, and they are more related with Pop-2 stellar population, and so the mass of white dwarf is typically less than 1 solar masses. This novae obviously eject gas into the space with delta T between 1000 and 100,000 years, and so novae contribute to the chemical enrichment of galaxies. The mass of the shell are of the order of between 10 to -4, 10 to -5 solar masses per outburst. Now, if we know the value of the galactic nova rate, I mean the frequency of occurrence of this object, we can estimate the contribute of novae to the galactic nucleosynthesis. The galactic nova rate is a big issue. You see, there is an incredible number of measurements, and these are the more recent. The last one, before the last one was Zuckerman et al. Between 39 and 51, but the real last one, that is probably the correct one, is in a recent paper with Alan Shaft and Starfield. 30 novae per year is a good number. So in our galaxy, we have a 2-core collapse supernova, or this is really order of magnitude estimate, but give you the right feeling. 2-core collapse supernova in a century, and in the same time, during the same time, 3,000 nova will explode in our galaxy. So we have to compare the 30-40 solar masses ejected ejected by 2 supernova explosion with 0.3 solar masses. What does it mean this? Well, it's not marginal. It means only that only nuclei enriched in the nova ejecta by a factor of 100 can contribute significantly to the galactic nucleosynthesis. And there are a number of these atomic species that are of interest. And particularly, I want to focus, and this is my last topic, on lithium. Why? Well, first of all, because these have been observed in the years, and this was never observed until a few years ago. Okay, let's think. Okay, one idea to estimate or to measure the primordial. Okay, I can go back here. The primordial abundance of lithium depend on the baryon photon density, and this is obvious. The larger is this ratio, the more reaction and more baryons will occur, and so there are more possibility to build helium-4, helium-3, and lithium. And one idea to measure, and these are the relevant reactions. So one idea to measure the primordial abundance of lithium was to measure the lithium inside, in the interior of very old stars, the halo stars of our galaxy. And this was done by this splendid French couple, Speed and Speed, in 1988 and 1990. They found that this plateau here are very, very low metallicity abundances. That is about 3 times lower than the abundances of lithium estimated by Planck. This is the plateau speed for obvious reasons. So with the modern measurement, we still have this, we can still observe the speed plateau. Here, the lithium abundance is determined by Planck, and these represent the cosmological lithium. How is possible there are stars that have less lithium that has been produced at the beginning? I'm not an expert on this, but I can understand that people is the argument is the following: lithium is very fragile element. At 1-2 millionth degree is quickly destroyed, and 1-2 millionth degree temperature is let's say are conditions that are easily detectable, are easy to find in the interior of stars. So probably this depletion of lithium is due to the fact that original lithium has been destroyed inside the stars. But now there is the galactic lithium problem. What about these young stars that present an incredible overabundance of lithium, even up to a factor of 10. And this has clearly demonstrated in these papers. So people start to think about HB star, red giants, cosmic ray spallation, all of this together, not enough. We need a lithium factory in the galaxy. So initially there was this prediction by Sumner, Turan, Sparks, and Arnaud that they suggest that novae can be producer of lithium for the galaxy. These predictions have been adopted by Francesca D'Antona and Francesca Matteucci in the early galactic evolutionary chemical evolution model. And at this point, what was missing was to find the lithium in the spectra of the novae. Fortunately, at the end of the 90s, there was a splendid instrument, Pharos, that was mounted to the 1.5 meter and then moved to the 2.2. It was a spectrograph with a 50,000 resolution. And just for people that are not familiar with spectra, this is the last paper that I had the chance to because then Rosino passed away, to write with Rosino and Takashi Ishima. Look at the spectrum of this nova. This is basically 1,000 delta lambda. And you see we could identify a few atomic species. Look at what happened with Pharos. These are only 400 angstrom, and you see how details are the spectra that we could have with Pharos. So we start with this. We're looking for lithium, no success, and we were just able to put an upper limit. The hunt for red lithium is not a funny title because the lithium line falls at 6,000 angstrom, so it's red, really. So we were making all this study of follow-up of novae, no lithium at all. Finally, thanks to the magic touch of Luca Izzo in 2015, we were able to detect for the first time lithium in the spectrum of novae. This is really a nice, okay, let's go. First of all, it's not a case that we found lithium in one of the closest novae occurring in our galaxy, at least according in our galaxy during the lifetime of astronomers. This is the brightest nova of the present century. In the meantime, Pharos was at the 2.2 here, and 319 atomic species were identified. And obviously, since the ejecta are in expansion, we have to know very well, to measure with a great accuracy what is the correction due to the Doppler effect. So at the beginning, we focus on well-known absorption line, like the sodium doublet at 5890 and 5896 in the rest frame. And this imply a correction for the shift of minus 550 kilometers per second. Then we use a calcium, 550 kilometers per second as well. Potassium, 560. So 550 was the right ballpark. And then this is the lithium here, when you correct for 550 exactly. Got it. Okay. So that was an incredible first detection of lithium. Francesca wrote on here, explode, this I liked it, exploding laptop battery in space, spinning lithium sparked by nova is fantastic. Scientists solved the mystery, etc., etc. This was when I was in Munich in 2008, they put on these newspapers, lithium first time, even the New York Times. Don't ask me how it was possible, but the New York Times reported. I have to tell you that 1 week later or 2 weeks later appeared an article in which they were commenting about the lithium as a medication for depression. Right. So I don't know if it was some link, but maybe, I don't know. What is more important is that an independent, I have 5 minutes. I have an independent team. They confirm on a different object the presence of lithium, not directly as we did, but by observing beryllium. And beryllium decay into lithium with a half time of 53 days. And this is reasonable because it's much easier to find, to detect beryllium than lithium, because lithium is really fragile. So the temporal window in which you can detect lithium is very, very narrow. This is, for example, 2 novae in the small Magellanic clouds that show an incredible presence of beryllium. This is a paper with Paolo Molaro. We detect beryllium in Rs Ophiuchi. This is a recurrent nova, is a subclass of novae. Okay, this is the point. When we consider the measurement of beryllium from a bunch of novae now, and that the half-life time is 53 days from the amount of beryllium that we observe in the novae, we can estimate that every nova outburst produce 2 times 10 to minus 9 solar masses of lithium in one outburst. And now when you consider the rate of novae, you can now see that we are able to reproduce completely through the nucleosynthesis model the overabundances of lithium that has been measured in young stars. And so my conclusion is that the lithium yield derived from the 1369 and all the other novae in which we have observed beryllium extended to the all Milky Way novae is sufficient to explain the overabundance of lithium in young stellar population. And now there are a number of papers that are focused on this aspect by Matteucci, Romano, and Grisoni. So galactic lithium problem solved. I stop here.
Thank you very much, Massimo. This was